So last time we talked about different ways to solve equations, particularly elimination and substitution. This time around, we're going to talk about graphing to solve systems of equations, as well as what it means to actually find a solution to a system of equations. Now, this is useful to understand what we're doing in concepts, but also sometimes the SAT will directly test it. So it's very useful for both reasons. Now let's start off with a simple example. So here we have a system of equations, and I want you to take a minute to try to solve it on your own. Now this one will work very well with either elimination or substitution. So go down below, click pause, try it for a minute, and then hit play once you've gotten to a solution. Great job. So if you're able to get it, you should have gotten x equals 1, y equals 1. So if you're a little stuck, feel free to go back to the last video and try it again. Now let's see that solution visually. We see here our system of equations and the graphs paired with them. So here we have y equals negative x plus 2, and we've graphed that in blue. And then in red, y equals 2x minus 1, and we've graphed that in red. So we have our solution x equals 1, y equals 1, and we can see here now that that's where these lines intersect on a graph. And so this is the essence of solving a system of equations, which is that when you find the solution, they're not just these magical numbers that mean nothing. They represent the point in x and y that satisfy both equations, and thus are on both lines. And that's what we're seeing here with the solution here at x equals 1, y equals 1. Now this is true even if we had some crazy wacky set of equations out there or graphs. And so we don't even need to worry about the equations sometimes, and we can really just all do it visually looking at the graphs. So in this case, we have these blue and red graphs of really wacky, weird equations we're not going to worry about. But if we could look at it, we can just point out to where the lines intersect, and those are the solutions. So here we have solution 1 at negative 2, 2, and here we have solution 2 at 3, 6. Now, this is also true even if we add more than 2 equations. So let's go ahead and add a third line in here. Just going to be a simple line like that. And now we can look at the solution to all 3 graphs, which would be, careful this time, it would be where all 3 intersect, not just 2 out of the 3. And so in this case, we only have one solution, and it is that first solution there, whereas the second solution and also this other intersection are no longer solutions to the system of all 3 graphs. So let's think back to simple equations with straight lines, and we're going to talk about number of solutions to these systems of equations. So the example we started with had just one solution. However, what about having 2 solutions, or 0 solutions, or even infinite solutions? Are these possible? We're going to look at those cases now. The one we started off with, y equals negative x plus 2, y equals 2x minus 1, we see our solution at 1, 1, but if we change one of the equations, so we're going to change the blue equation here, we see how our solution changes to 2, 3, but still just one solution. We see how changing these 2 lines just changes the one point at which they intersect. But let's try to do something tricky. Let's see what happens when we make these lines parallel like we see here. So remember, parallel means these lines have the same slope. So in this case, we both have slopes of 2, but different y-intercepts. So graphically, like we talked about before, we can see that these 2 lines never intersect, and thus we have 0 solutions. Now, though we can see this graphically, we can also see it numerically by trying to solve the system of equations. So let's try to do that using elimination and see what happens. So now let's solve and see what happens. So let's use the method of elimination we covered before in the last video. So we're going to subtract our equations, and this is really easy. We already have the variables lined up and matching. So we subtract, and we see the y's cancel, great, y minus y equals 0. And then we also get the x's to cancel. Now we haven't seen this before, and what it gives us is something quite strange. We have 0 equals 3. No x, no y. We have an equation with no variables, and in fact, 0 of course does not equal 3. So we're left with this equation that makes absolutely no sense. And so that matches with what we saw graphically, which is that there is no solution, because there is no x and y that make 0 equal to 3, of course. And so that's how we see there is no solution to this system of equations. So let's apply this new knowledge to an example of a problem that we should expect to see on the SAT. So let's look at an example of this problem here. Now take a second to read through it. And at first glance, you might be afraid that we have not 2 equations here with 2 variables, but 2 equations with now 3 variables. But it's okay, because we are told that we are supposed to find no solutions, we actually can solve for the unknown here, which is b. So let's go ahead and solve our problem. So we know from before that to get no solutions to a system of equations, we need to have both the x's cancel and the y's cancel. So in this case, it's going to be pretty easy to get the y's to cancel. We just subtract our equations and we get y minus y gives us 0. Now the x's are where it gets a little more interesting. So we have bx minus negative 3x. So that's going to give us b plus 3x, and then we have, of course, our minus 2. And so what we need to make the x's cancel is for this b plus 3x to go away. So to do that, we see we have to have b plus 3 is equal to 0. And based on that, we conclude that b equals negative 3, and thus we found our answer. b equals negative 3 gives us no solutions to this system of equations. So let's look at a similar example. So note this problem looks very much like the one we saw before, except now instead of dealing with no solutions, we've been asked for infinite solutions. So let's talk about what that actually means. Here we see an example of a system of equations that will have infinite solutions. We see both the equations, which happen to be exactly the same, and the lines, which are overlapping. And that's no coincidence. We see that because these lines are the same and they completely overlap, any x and y are going to satisfy both equations. And that's what it means to have infinite solutions to a system of equations. So let's apply that to our problem here. So we just saw that to have infinite solutions means to have the same two equations. So if we have the same equations and we subtract them from each other, then we should of course be left with 0 equals 0. So we can apply that to the problem here kind of in the same way we did for no solutions. So let's subtract our two equations here, which we want to be the same, and show that they have to go to 0. And so we get y minus y goes to 0 easily like before. And then we have b plus 3x has to go to 0 also to get 0 equals 0. And so just like before, we get b plus 3 equals 0. And like before, we have b equals minus 3. And there we're done. So putting it all together, we should know that to solve any system of equations or graphs, we can just look at where their graphs intersect, and that is the solution or solutions. And we also saw that systems of equations can have either 0 or 1 or infinite solutions. And when we're trying to figure out which one, we should look at whether or not the equations cancel when we eliminate fully. Hope you liked the video. If you want to hear more and see what else we're up to, hit like and subscribe, and see a new video coming out from Point Avenue every week. If you want to talk to us, hear more about what we're doing, or have any questions, email us at contact@pointavenue.com. Bye!